All right, ladies and gentlemen, day 2 of graphing lines and linear inequalities. I've got a little bit more to talk about with graphing lines, some kind of special cases, and then just one more example, kind of normal example, and then we'll dive into graphing inequalities and some other things. So we're just going to pick up in our notes where we left off. But I'm going to give you 2 examples in this next example. We're going to graph 2 lines. We're going to graph lines y equal 2 and line x equals -3. Okay? Now, we're graphing lines. So each of these represent a line that is at y equals 2 and a line that is at x equals -3. Well, here's the thing. A lot of teachers will just tell you simply, well, here's the thing. Y equals 2 is horizontal. And you're just supposed to know that. And then x equals -3, that's going to be vertical. But you know what? If that's the only way you learn it is if you're just told which is which, and it's just really hard to remember. So what I want you to recall, if you forget about these, which one's horizontal and which one's vertical, I want you to think about if you were to make a table. If you were to make a table of values to help you graph y equals 2, well, you would notice y is always what? 2. And since there's no x, x can be anything it wants to be. X could be -2, 0, +2. It doesn't matter. And what you notice is when you graph those coordinates, -2, 2, 0, 2, 2, 2. Oh, whoops. -2. 2, that's better. But when you graph those, you quickly realize, oh yeah, if I connect those, that's going to be a horizontal line. So again, if you forget which one's horizontal and which one's vertical, make yourself a little table of values, fill in what you know, and then I think it becomes apparent pretty easily. Let's go ahead and label this because we're going to have 2 graphs. So let's write y equals 2. And label that graph. And then again, if you go to x equals -3 and you can't remember, oh my gosh, which one is that, horizontal or vertical? Well, make a little table of values, but what's x mandated to be? It's got to be -3. But y can be anything you want it to be. It could be -2, 0, 2, doesn't matter. And when you plot those points, you'll see, so -3 down 2, -3, 0, -3, 2. You quickly see that if you connect them, they're a vertical line, like so. And that was at x is equal to -3. So hopefully that kind of helps you to differentiate. But whenever it says graph a line and you only have one of the variables, an x or a y, it's either going to be horizontal or vertical. All right, moving along, just to make sure we've got another example here for you. Let's graph 2x plus 5y minus 15 equals 0. Well, this is sure going to be easier to graph if it was written in slope-intercept form, so let's focus on doing that. We'd like to get y by itself. I could divide by 5 first, but I have to remember to divide everything by 5. I'm instead going to get rid of the things that are being added and subtracted to it. So I'm going to subtract a 2x, move it over. I'm going to add a 15, move that over. And I'll get 5y is equal to -2x plus 15. Is y by itself yet? No, it is not. We're going to divide by 5. And I want you to distribute that division across the addition. And we're going to end up with a slope of -2/5 and a y-intercept of 3. And from that, I can graph. So start with your y-intercept of 3. Get your first point. You can get a second point by going down 2 over 5. And 2 points is enough to determine a line, but I want it to be pretty accurate, so I want to back this up. I want to go up 2, back 5. And that'll cover the page pretty good right there. And there you have it. We've graphed a line. Now, I'm trying to make a point to start talking about this earlier. Domain and range. Now, what's interesting about x equals -3, your domain, your set of all x values is just -3. That's your domain on that one. Your range, though, goes forever in all directions, so it's going to be all real numbers. Kind of interesting. For y equals 2, your domain, or your set of input or x values, is going to be all real numbers, goes on forever. But your range does not cover everything. Your range is your output or your y values, and the only y value that exists is 2. So it's kind of interesting. Down here, it's a more typical sort of line. It's going to go forever to the left, forever to the right, forever up, forever down. So for your domain and your range, they're both going to be all real numbers. All right. Well, let's move on. What else do we got here? Let's flip it over. Oh, we got some blank space here. All right. So, what I want to talk about here is there's another way to graph without using a table and without using slope-intercept form. There's a third way to graph, and we want you to be familiar with it and be able to use it. So, for our next example here. We're not actually going to make a graph, but I want to show you what you would do to do this. I'm going to ask you to find the x and y intercepts of the lines. So I'm not actually asking you to graph, even though you could do this to graph, but we'll do 2 examples here. We've got an equation of 6x plus 4y equals -5. And B, our equation is 2x minus 4y equals 2 times y minus 8. And we want to find the x and y intercepts of these lines. Well, we could get the y-intercept by rewriting them in slope-intercept form, because the intercept on slope-intercept form is a y-intercept. But that doesn't help us get the x-intercept whatsoever. Well, let me show you something real quick. Let me flip this over. Okay. The y-intercept happens to be where x's value is 0. When x's value is 0, that gets you the y-intercept. The x-intercept is where y's value is 0. Okay, so this one was at 0, 5. This one is at, it looks like 2.5, so it's 2.5, 0. But we're going to use the fact that these both have zeros in conspicuous places. We're going to use that to help us out. So take a look here. When you're asked to find x and y intercepts, I want to see you do this. I want to see you write out x-intercept, y-intercept. And from there, for the x-intercept, that's going to be where y's value is 0. The x-intercept is where y's value is 0, like I said just a minute ago. But you actually put it into your equation and then solve it. 0 times 4 is 0. 0 plus 6x is 6x. divide by 6, and our x-intercept is at negative 5/6. Now, a lot of teachers will accept this. I prefer it if you actually write out for the x-intercept a coordinate. It's a point. It's negative 5/6, 0. To get the y-intercept, that's where x is 0. So you go 6 times 0 plus 4y equals negative 5. 0. 0 plus 4y is 4y. Divide by 4, and we get a y-intercept of negative 5/4. And I would like for you to show me that you really understand this by saying 0 was the x value. Our y-intercept is, the y value there is negative 5/4. And those are really solid answers. Again, I mean, you know, I guess I'll have to accept that, but I would actually prefer your answer to be that. Now, you might be tempted on B to simplify a little bit, and you could. There's no problem with that. But I would just, I don't know, I'd assume just go right into x-intercept, y-intercept, and do like we were saying, for the x-intercept, you put a 0 in for y. Like so. Clean it up a little bit, 0, so we just get 2x. Inside here, we do the parentheses first, so we get 0 minus 8 is negative 8. 2 times negative 8 is negative 16. Divide by 2, and x is equal to negative 8. Or you can write it as negative 8, 0. That's your x-intercept. For your y-intercept, put 0 in for x. So we get a 0, leaves us with the negative 4y. And then on this other side, well, it's kind of funny. I mean, I guess, yeah, I guess I'll go ahead and distribute 2y minus 16. Now I'll get my y's together. I'll get a negative 6y equals negative 16. Divide by negative 6, divide by negative 6. I will simplify that a little bit. Negatives divided become positive, and 16 and 6 have a common factor of 2, so we can divide those out. We get 8/3. And again, y-intercept is a coordinate, so I want you to think of it as 0, 8/3. Okay, so at this point, let's transition to graphing linear inequalities. And you know what? You can still graph using slope-intercept form. You're still going to have, you know, a slope and the y-intercept, and it's going to be very similar graphing. You're still going to have horizontal lines, vertical lines, depending on if you only have an x or a y. And but there's some added things here. Okay, so what I'd like for you to do is write out graph linear inequalities. And I'm going to make this a two-step process. Step 1 is to graph what I'm going to call the boundary line. Graph the boundary line. And when you graph your boundary line, you're either going to use a dashed line or a solid line. And here's how you're going to know. Use a dashed line for greater than and less than. Use a solid line when you're dealing with equal to's. So for greater than or equal to and less than or equal to. Okay? And this kind of makes sense. If it's just greater than, that means you don't get to include that boundary line. You go right up to it, but you don't include it. And then same thing for less than. But if you have the equal to, you want to make that a solid line because you want to actually include that line. And for step 2, I'm just going to say shade accordingly. Shade accordingly. We'll go into more detail about that here in a second. Let's start out with this example down here. Let's graph y. Oh man, excuse me. Y is less than -1. And I'm hoping it's still fresh in your mind that if there's a y and no x, this is going to be a horizontal line. So we're going to draw a horizontal line through y is -1. Now here's the thing. We got to decide, is this going to be a solid line or dashed? Well, because it can't be equal to it, we got to dash that thing. Oops, dash it. Well, okay, I kind of messed up, but you get the idea. Put arrows on there. It's important to put arrows. And then I said shade accordingly. Well, to me, it makes sense. This won't always be an opportunity, and so I gotta be careful here, okay? When y is by itself like this on this side, and you graph it, or x is by itself on one side and you graph it, you can just use your common sense here. It says that we want to shade y is less than -1. Well, where on the graph are things less than -1? Well, they're downward, aren't they? And that's exactly where you're going to shade. And I just kind of like to just shade it real quick. Be careful not to cross your boundary line. You know what I mean? But you do want to get right up next to it, and you just shade. And it makes sense to me that you would shade below. But later on, if you go into more involved mathematics, you're gonna, on some instances, you're gonna have to use a test point. And what I mean by that is you just pick a point, and if it works in your equation, or inequality I should say, if it works, you know that that side needs to be shaded. If it doesn't work, you know that by necessity the other side will need to be shaded. So for example, I chose a test point of 0, 4. Well, the x value of 0 doesn't do anything, but I would put a 4 in here. And is 4 less than -1? No, it's not. So by default, I shade the other side. Commonly, people just like to use 0 if at all possible, because it's just easier to deal with. Is 0 less than -1? No, it's not. So you shade the other side. It's using a test point. Now, the domain and range are kind of cool here. The domain is our set of x values, and notice our x values go forever, left and right, so it's all real numbers. But our range is our set of y values, and notice our y values do not go above -1. We don't count anything like that. So what we can do is we can use an inequality to write this. Our range are y values that are less than -1, which is interestingly enough what we were asked to graph, which is kind of cool. All right, let's turn the page. 3 more examples here, and then we'll be set. Let's graph 2x is less than or equal to 8. Well, to graph this, I'm going to go ahead and get x by itself. Divide by 2, divide by 2. X is greater than or equal to 4. And I don't have a y value. I just have an x value. This is going to be horizontal at x equals 4. Solid line or dashed? Well, because it's equal to, I'm going to make a solid line going through there. A solid line. And then I'm going to use And once we've got our line drawn there, then we need to shade. And let's think about this. X is greater than or equal to 4. Well, where are we going to be greater than 4 on the X values there? To me, that's pretty clear. It's going to be to the right. So we're going to shade to the right. And be careful. Don't do like I did. See how I crossed over there? That's a no-no. Don't do that. Okay, but shade to the right. Now again, sometimes you won't always have just an X or just a Y over here, and you'd want to use a test point. And so, for example, if I use 0, 0, if I put a 0 in here for X, is 0 greater than or equal to 4? No, it's not. Shade the other side. If you did 5, 0, put 5 in there. Is 5 greater than 4? Sure it is. And you know that from your test point which side is going to be graphed. Whenever you graph these, you know that half of the coordinate plane is going to be shaded, okay? If you were to zoom way out, you would see, oh yeah, half of this thing is graphed. So that's kind of the idea. All right, let's move on to another one here. Let's graph 3x minus 2y is less than or equal to -6. And to graph this, we've got an x and a y, so this is kind of more standard operation here. I'm going to do slope-intercept form. I'm going to subtract the 3x over, subtract the 3x over, get -2y is less than or equal to -3x minus 6 to get it in slope-intercept form. And then I have to divide by -2, and I want to distribute that -2 across the subtraction here. Now, try not to forget, I just divided by a negative. What does that do to my inequality symbol? Yeah, that's right. It flips it. This is going to become 3/2 x. This is going to become a 3. And now I'm ready to graph this using slope-intercept form. My y-intercept is 3, and then from there I use my slope, up 3 over 2, up 3 over 2. I can back it up. Down 3, back 2, down 3, back 2, down 3, back 2, down 3, back 2. Solid line or dashed? Well, because it's equal to, we're going to use a solid line. Like so. And you know what? I think I can still make sense of this because y is by itself. Which side of the line is going to be the greater than y? Are the y values greater this way? Or are the y values greater this way? Well, y values are up versus down, so I'm going to be shading y is greater than y. I'm going to shade on this side because it's greater than. Okay, and because I'm dealing with y, I want to think up versus down. Do I want to shade up or do I want to shade down? And I want to shade up, up. So just go right there on the line and move up. Greater than, up. Which side are you shading? Boom, you got it. Again, though, you could use a test point. If I were to use a test point at 0, 0, 0 is greater than or equal to 0 plus 3, which is 3. Is 0 greater than or equal to 3? No, it is not. I then have to shade the other side, okay? And then one more, just for good practice here, one more, make sure we got it. Let's graph x minus 3y is greater than -3. To graph this, I'm going to use slope-intercept form. So I am going to subtract an x, leaves a -3y behind. I'm just subtracting an x, I don't flip the sign. And then I'm going to write -x minus 3. But from here I'm going to divide by -3, divide by -3, divide by -3, distribute that division. I do have to flip the sign. Negative divided by a negative is a positive. I'm going to make this 1/3 x plus 1. My slope is 1/3. My y-intercept is 1. Up 1 over 3. Up 1 over 3. Down 1, back 3. Down 1, back 3. Solid line or dashed? No equal sign. So I'm going to dash it. And y is less than. Well, would it make sense to shade above or below if it's less than? It makes sense to shade below. But again, you could use a test point. I'm going to use 0, 0. If I put a 0 in here and a 0 here, is 0 less than 1? It sure is. That's the side that I'm going to shade. All right, so now you're prepared to finish up that handout we've been working on. Thanks so much for watching.